Hello and welcome everybody to today's webinar on the segmented multipass cell that we recently introduced as IR suite. We call it the IRcell-S. Today I'm here with my colleague Martin Statelov, who is in charge of manufacturing and assembly here at IR suite. He'll be showing the experimental part, and my name is Marcus Geiser. I'm one of the co-founders of IR suite, and I'll before give a brief introduction. That is already the agenda. So the first 5 minutes will be a bit general about multipass cell, the history, the purpose, and what are important design parameters. Then how we think we achieve that with the IRcell-S, and then of course go over to the main part, the live demo, which will be first showing you a bit the products themselves, the two sizes of the IRcell-S, then go over the setup and the individual components so that you get a feeling how we set up here and also what we recommend, how to set up the multipass cell, do fringe analysis, and then also show you the setup of the cell from scratch. So starting with the theoretical part, multipass cells are used in absorption spectroscopy to exploit basically Lambert-Beer's law, which says that if you just exponentially absorb the intensity of light that is coming in, so if you increase the interaction lengths between light and your analyte, you will have stronger absorptions. And if you look at a very weak signal, you want to have as long as possible interaction length between the cell and your analyte. Historically, this concept has been around for a very long time. This is not a complete historic review, just some main milestones. Of course, the white cell has already been developed in 1942. It's still to date very successful. It's used a lot with FTIRs due to its tolerance to very high numerical apertures. Downside of that is a bit the large internal volume that you have in those cells. A bit later, the Harriet cell was developed in the 60s. This was originally intended to be a delay line, an optical delay line, and not a tool for absorption spectroscopy, but it was used as exactly that later on as well. An advantage here is that you can have smaller volume per path length, but you can only couple beams with a bit of a smaller numerical aperture. And the design that we're going to be talking about today is the circular multipass cell, originally developed in 1994 by Thoma et al. Originally intended for the use in shock waves, which are tools that are used for combustion diagnostics, but I think not used that much due to some design challenges related to the optical resonator design that we'll talk about in a bit. And there was a lot of follow-up work done on that by my co-founder Markus Mangold in the Emmenegger group at EMPA, and even more in the Emmenegger group at EMPA by Manuel Graf, as shown in these publications. And also our IRcell-S, of course, is a further development in that direction. What is the design space for multipass cells? What are people trying to achieve? Well, of course, first of all, it's used to have a long path. Doesn't mean as long as possible. It really depends on what is the absorption strength that you have in your system, so that with the available path lengths, you get a reasonable absorption signal, you don't saturate. This, of course, is to increase the sensitivity. The second parameter is low volume, physical volume. That has two advantages to have a low volume. The first one is to have fast response time, because if you have a given amount of analyte that you can use to flow through the cell, with a smaller volume, you'll have faster gas exchange. And the second advantage is if you're constructing an instrument, you want to have a small footprint of the system. The third parameter, of course, is low fringes. That is essentially crosstalk between different possible paths in the cell, but also in the whole optical setup. And of course, the lower these fringes are, the higher the sensitivity will be that you're getting. And a more practical aspect is robust and easy alignment. And and that just makes the cell convenient to use and relaxes a bit the requirement on the setup around the cell itself. To set up the cell, of course, the key components are the mirrors that construct the resonator, and as you see here on the right, this is just the well-known stability diagram of a resonator that is constructed of two mirrors, and you see that depending on the curvature and the arrangement of the two mirrors, you get a stable, marginally stable, or an unstable resonator. Unstable resonator means that light will not propagate well on a closed loop when you keep sending it through the cavity. Now, if we look at what the optical design of our original first IR cell was, it was round, or it is round. So by construction, it was using a concentric resonator. And while this is good to manufacture and useful for circularly symmetric experimental environments, the challenge is, as you see pointed out here, that this design is just by default or by construction really at the edge of the stability diagram. So any deviation from a perfect shape or any deviation from a perfect beam will just amplify and propagate through the cell, which makes it difficult to align if you have any instability around. This is also one of the main reasons I think the cell was historically not used so much before an absorption mask was introduced. And this is what you see here on the picture to the left. It's an IR absorbing mask placed in front of the mirror that only leaves those spaces open, which are intended for beam reflection. And with that, you could suppress the fringing sufficiently to make the cell usable. And this is then what we offered as the first version IR cell. Now, of course, it would be nicer to have something stable so that we can get rid of the mask and just have many other advantages in alignment and stability. And that is the IRcell-S. So it's exactly what it's doing. So we change the radius of curvature at every point where we intend the beam to reflect. So you see this in this drawing here on the left, that we define a star pattern with a maximum density and have an individually shaped mirror at each of those positions. And by doing that, we can go away from the marginally stable resonator and create a fully stable resonator, which just relaxes the requirement on the beam and the alignment quite a bit. In reality, the cell looks like you see here on the photo to the left. You have in different sizes a different number of segments. The segments are typically 5 millimeters in each dimension, height and width, and you are somewhere towards a confocal resonator with those cells. So what are the advantages of this product? First of all, compared to the previous generation, we can reduce the volume and also increase the path lengths. We can increase the path lengths because just the beam pattern is more stable, so we can tolerate more reflections and a longer path length. So now we offer this at 4-meter path lengths, 31 milliliters, and at 15-meter path lengths with 128 milliliters volume, which is quite low for these path lengths. We still specify fringe level below 2 times 10 to the minus 4 RMS, and in practical terms, really, it is a huge difference, a huge upgrade. The coupling angle tolerance is quite large. It's actually a large fraction of a degree compared to something like more of a milli-degree in the previous generation. Also, the tolerance on the numerical aperture of the in-coupling beam is relaxed. You can work with a collimated or a focused beam, whatever is more convenient for you. And also the alignment is quite straightforward. We don't even use a red co-alignment laser anymore when we work with the IR, and it's really a matter of getting light through the cell. It's a matter of a few minutes, as we'll show live now. Also, we could remove the absorption mask, which is advantageous for a few customers that were concerned with adsorption to the IR absorbing Teflon before. So this problem is removed, and also at the same time we introduced separate apertures for coupling in and coupling out, so that you can place your components for coupling in and components for coupling out on opposite sides of the cell to just make the design of the setup or the instrument a bit easier, because the coupling angles are almost normal. So placing the components for coupling in and coupling out, you would have to place them quite close to one another, and this is relaxed with the second aperture. So we'll proceed shortly to the experimental part, and Martin will show the individual products. Just before briefly the specs. So the two versions are 4 and 15 meters. That's what I said. Also, the path length on this is variable. That means the mirror pattern that we have in the cell supports multiple star patterns of the beam. So you can also have shorter path lengths in each of the cells when you use a different coupling angle. Also, the in-coupling apertures, 5 millimeters, just like the previous version. And the dimensions maybe matter, so it's a bit more than 10 centimeters for the small cell, almost 20 centimeters for the big cell. But I don't think I'll repeat more of this table, but instead hand over to Martin to show you the actual thing. So on to the experimental part, and I will switch the sharing to the camera. Just a second. Right. So Martin will be doing the experimental demonstration. I will be following with the camera. If you have any questions on the way, please post them in the Q&A tab, and we'll answer them, try and answer them at the end of the webinar. So please, Martin, go ahead.
Thank you. So now we move on to the live demonstration. So today we would like to show you a few things. So we will start with showing you quickly the cells live. Then we will move on to the optical setup that we use. We use this to characterize the multipass cells. Then we will explain to you how we quantify the optical fringes. And at the end, we will showcase how easy it is to align the cells. We will do this from scratch. So as a starter, let's look at the cells. So here in the setup already, we have a 4-meter optical path length version of the IRcell-S. And you can see probably the individual segments. Now on the right side, this will be a little bit more visible. We have the 15-meter variant of the IRcell-S. So this is roughly 20 centimeters in diameter, and you can see the output and input aperture. You can also see all these segments, and then behind it we have fully assembled the IRcell-S 15, and then you also have 3 gas fittings for inlets and outlets and the sensor. Then for the input and output aperture, we have a window holders, and here we basically mount half-inch windows of choice. We can do many choices, IR coating and wedged. Then this one, before assembling, so this is how you would use it when you actually set it up in your setup and you want to align it without the lid, and then you can just close it with the lid. Great. Now we will move on to the optical setup that we use. So we use the setup to characterize the cells, and we do this for every cell. And the most important thing that we do is to quantify the optical fringes to make sure that they are in spec with what we have in the datasheet. This setup is also good to go over, and we will go over step by step, because it is good to know roughly the optical elements that have to be set up so that you really reach the low optical fringes, and also that you know how to basically use the segment itself. So we will go from start here. This is quantum cascade laser or QCL package in a stable environment. It is emitting at roughly 4.3 microns, Right after that, we have a lens to collimate the beam, so that we have a nicely collimated beam throughout the setup. Right afterwards, we have a neutral density filter. This is just to reduce the optical power because we have very sensitive detector. Right after that, we have two mirrors. And with these two mirrors, we make sure that the beam is in the correct height. And the correct height means the same height as the segment itself. Not only that, but also we have to ensure that the beam goes parallel to the optical table or parallel to the horizontal plane of the cell. After that, we have two lenses which make a telescope. In our case, we reduce the size of the beam roughly three times, and this is quite important to have low optical fringes. It is important to have the beam size or beam spot smaller than is the dimensions of the mirrors in the cell. And the dimensions are 5 by 5 millimeters. So we recommend to have the beam spot definitely below 5 millimeters, best is to have somewhere between 2 or 4 millimeters. In this case, we go in with a collimated beam. It is also possible to go in, couple into the cell with a focused beam. Right in front of the cell, we just have a mirror mounted on the kinematic mount, just to be able to fine-tune the direction of the beam into the cell. Then we have, now we are already coupled to the cell. We'll do this from scratch later on. We'll show you how to align this. And basically, the light goes to a certain, so when you do the alignment, the beam has to first hit a specific mirror, and after that it will bounce off each mirror exactly once. So in the case of small cell, that will be the 4-meter version, that is 46 times, and in the case of the big cell, it's 86 times. After the cell, the beam goes out through the output aperture, and in this case, we have a collimated beam before, so we have also collimated beam after. And then we just use a concave mirror to focus the beam onto the detector. And then we have the detector to collect the light. Now that we have a roughly picture of the setup, we will explain how we quantify the fringes, because this is important to achieve good sensitivity and to have low noise in the measurements. So to do that, we will now move onto our monitor, which we use in this setup. And now we have to start with the QCL laser. So we don't have the QCL laser at a stable current, but what we do is that we sweep the current of the laser in a certain shape. So in particular in this waveform. So here on x-axis is time. The entire range is 10 milliseconds. So the frequency is 100 Hertz. Then on the y-axis, we have the voltage or the current that we put on the QCL. What this means is basically, as we change the current, as we sweep the current, we also sweep the wave number. Because for QCLs, if you change the current, you will also change the wave number at which the beam is emitting light. Now, if we move on to the signal that we see from the detector, we will see this. So now we have a similar graph or similar plot. On x-axis, we have again time axis. So this is the same 10 millisecond interval. And on y-axis, this is x-axis, and on y-axis, we have the amplitude of the signal. So because we sweep the current, we also sweep the intensity of the beam. Therefore, you see the same shape here as the waveform which would drive the current, the same sweep. Now, to qualify the fringes, two things, we have to do two things. First thing is we have to convert the time axis into a wavelength axis. And this is because basically every point on the time axis corresponds to different current on the laser, and different current on the laser corresponds to different wave number. So basically this we can convert this axis to wave number axis. And then on y-axis, we have the signal from the detector, and what we want to do now is to quantify the optical fringes. And how we do that is basically the optical fringes or the noise in the setup. It's basically are basically deviations from this monotonous part that we see on the plot. So this is the deviations from the waveform with which we drive the current. So the first step to quantify the optical fringes is basically to fit this monotonous part with a certain order polynomial. And when we do that, we will get what remains will be when we fit it and subtract it, we will remain with the modulations on top of that. And in this plot is exactly that. So this is fitted and subtracted the monotonous part. And what remains is the modulation of top of that. In this case, we see optical fringes with some different frequencies. Now to quantify that, we have to make a measurement and then we run a script to do that. So we will take a few second measurement. And then we go on to the script, which we will run, which will take a few seconds to run. So here we have it. So first, we will look at this plot, and this plot is basically what I just have shown. So this is this plot. So this is the signal from the detector, but subtracted the monotonous part of this shape. So we now have the modulations or the noise that we have in the optical setup. From that, we do a Fourier transform of this, and that looks like this. If we zoom in a little bit, we will see now basically contribution at different path lengths. So we have a few peaks, and at these peaks we have optical fringes. Now, what we are interested in, of course, is what is the we want to quantify the optical fringes, so we want to know how big the noise is, and we want to plot this as a function of spectral coverage, or spectral coverage, spectral resolution rather. And of course, if you have broad spectral resolution, then you will have this, some of the optical fringes may average out and you will not see it, but if you have very narrow spectral resolution, then you will start to see effect of these fringes or this noise. And this is exactly what we do in this last plot. So here on y-axis we have the root mean square of the signal that we had just on the plot before. So this would be in per mil. And on x-axis, we have the wave number resolution. So again, as we go down with the wave number resolution, we have higher optical fringes or higher noise. And for every cell that we ship, we measure this plot and then make sure that we are always between the value that we specify, which is 0.2 per mil. So that is with optical fringes. Now, of course, if you have some questions, feel free to put that into Q&A. And then at last, we would like to show you and demonstrate how easy it is to align the cell. So right now, we have the 4-meter variant in the setup, but we will remove that. And we will put the 15-meter version instead. And we will align it. Right, so now we will remove this cell. If you look at it from the bottom, we have it mounted on 3 posts that are set to certain height. We will take them off now, so these are basically the 3 M6 threads that you can use to mount the cell in your setup. I will use these posts to mount the other cell, and this is basically the first thing you would have to do, and that is make sure that your cell is at the correct height, and also that is parallel to your optical setup. Of course, now assume that you already have a beam that is collimated or focused at a certain parallel to the optical table, and that is small enough. So now the big cell has the same threads. So now we'll just mount it. Same posts. And now we will put it into the setup. And inter-alignment usually lasts around 5 minutes, even on the first try, not counting in setting up the optical setup. So now I'll put it in. Good. So remove this now, and now you can go for the alignment. We'll remove the ND filter so that we can actually see the beam with the thermal paper. And now basically we already have the beam at certain height, and it's smaller than the mirror segment. So first thing you have to do is you have to make sure that the beam enters through the input aperture, and it enters roughly or quite nicely through the middle of the aperture. So now with the thermal paper we can see the beam, and now I'm just trying to align it so that the beam goes through the middle of the hole, which is already the case. Then the second thing is, and that will be all, is to hit the right mirror. So the first mirror has to be a specific mirror, and the mirror is basically always a second mirror from the output aperture. And this is the case in both versions, in 5 meter, 4 meter and 15 meter as well. So now if we look at the beam, we have the beam right here, and the hole that we have to hit is second from the output aperture, and second counting to left or counterclockwise. So it would be this one. So right now it's not exactly there. So now I will slightly move the cell. Okay. To make sure that the first reflection is the second mirror. So the beam is actually here. And now seems to be roughly in the middle of the correct mirror. Now we can double check that we can slightly tune again. Of course, I moved a little bit the input aperture position, so I will slightly move it back. Now it's again in the middle. And so now we are going through the center of the input aperture and we are hitting the correct mirror in the middle. Then with the kinematic mount mirror, you can fine tune the position at which you are exactly hitting the position. Now that after you hit the first mirror, now basically the beam will reflect off that and will reflect off each mirror exactly once. That means you can basically look at every mirror and make sure that the beam is positioned nicely somewhere. For example, choose random mirrors. You don't have to look at everyone. If it's good on view, it seems to be nice in the middle and center. Then it will be already nicely aligned. Yes. Okay, so now that we made sure that we are hitting every mirror, we will already have a beam going out of the cell. So now we can see the beam already, and since the incoupling beam was collimated, we have again a collimated beam. So this was the alignment itself. Of course, after this, you can close the cell and then you can finish the setup after the cell, which means you can optimize your setup to have to focus nicely on the detector depending on your application. And I think that's pretty much it.
Mm-hmm. Yeah, thank you very much, Martin. So we can move over to the Q&A. I just have to rearrange the screen share. All right. So a few questions came in. First one is, what is the pressure range for the IRcell-S? So we specify it from 0 to ambient pressure. We don't have an overpressure version at the moment. This would require a redesign to make the window holders more pressure tolerant. I think the cell itself would be perfectly suited for high pressure applications. But we would have to redesign the mirror mount. And we're happy to do it if the application justifies it, especially for things like shock tube applications. This could be quite interesting. Second question is it possible to upgrade the original IRcell to the IRcell-S version? We can give, if you want the new cell, we can give a little bit of a discount on the old cell, but since we completely discontinued the old product, we're not going to be able to give you a full refund on the old one. But of course, we'll give you a little bit of a discount if you want to upgrade, because of course we would like people to work with the best possible revision of the cell. Then, very, very interesting question. Could it be fiber coupled to be able to connect in a process chemical lab environment? The answer is yes. We have coupled in light with fibers and collected light with free space optics. So it is definitely possible. We don't have a plug and play accessory for that. We are happy, however, to disclose the dimensions of the port and the requirements on the optics so that you can design your own tool. Or if you give us your requirements, we're also happy to validate in these specific applications for you. Next question, why the 3 gas fittings? That's usually inlet, outlet, and pressure sensor, but that's entirely up to the user. Actually, the top and bottom lid don't have much functionality besides sealing the cell and reducing the volume by protruding a bit into the ring. Do we have a top part here, maybe? Thank you. So, as you can see, there's a bit of a elevation on top of the lid, so that goes into the cell to reduce the volume. But that's entirely up to the user whether to use that or use the cell without the lid. So you can basically make your own flanges as you want, or we can make custom flanges for you if you don't like the 3 ports. What are the specifications of the QCL beam? Very good question. So it has a diameter of about 4 or 5 millimeters, and that is just dictated by the divergence angle of the QCL and how close we can go with the lens. The divergence I actually don't even know, because this is a manual collimation that we have here. So it's not a fixed factory-made package, but it's home-built for our purposes here. And then this leads into the next part of the question: when you decide a telescope is, when do you decide a telescope is required before injecting the beam? So you should go with a significantly larger beam than the element size of the IRcell-S. So this is about 5 millimeters, as Martin said. So we should, oh, so sorry, did I say larger? Yeah. My mistake. Should be significantly lower than that. So something on the order of 2 millimeters or a bit smaller would be ideal. If you're too large, you risk spillover from one mirror segment to the neighboring mirror segment, and that will be exactly a strong fringe. What are the gas temperature limitations? That's a good question. We don't fully specify this, so the coating that we have on the cell is quite robust. I think for a high temperature application, we would be interested in offering a test unit to find out how much temperature the unit takes. I think in a situation like that, you would probably also want to heat the cell itself to a certain temperature to avoid condensation on the surface. So this is not per se specified by us, but we'd be happy to look at requirements and try to get it work under the pressures and temperatures and with the substances given. Okay, there's another question. I think this was already answered. Is there an option to have a fiber port or fixed fiber? Again, yes, fiber coupling does work. There's no off-the-shelf solution, but we'd be happy to look at your requirements and recommend components or work on a flange for you. Next question is on the windows. Are the windows exchangeable? Yes, the cell typically comes with a window of your choice of any reasonable IR materials. They're not too exotic, they're included with the cell, and they are just clamped and sealed with an O-ring. So if you're used to handling optics, you can exchange them yourself with any 1/2 inch diameter, 5 millimeter thick windows. The windows are also available with a badge if required. So these were all the questions. Oh no, these were not all the questions. More came in. How do you adjust and identify different path lengths in a single cell? Is the path length known for each possible path? Yes, good question. Thank you for that. So this is just by choosing which mirror segment you hit first. I think you have the best insight about the design.
Yes, that's correct. So by standard, you hit a specific mirror and you get this 15 or 4 meter path length, and then of course you have different options for both of the cells have different options. And if you hit, we have this in the manual, so if you hit a different mirror as the first mirror, then you will get a smaller amount of reflections, and this means it's a smaller optical path, and we have exact numbers for the path length that corresponds to that. So for example, for the big cell, we have, I think, three different optical path lengths that you can achieve. And you can also go basically straight through the cell, just one pass without any reflection if that is desired.
Yeah, right. So yeah, it's actually, of course, once you have the cell aligned, it's not easy to see anymore how many mirrors you're hitting. But if you follow with the thermal paper from the entrance aperture to the first mirror that you hit, you can clearly see, is it the second one for the full path length or another one for a lower path length, and then you know which beam pattern you have. This is also outlined in the manual. Also these steps, the angle steps from like between coupling with one path length to another path length are significant because you have to shift by enough angle to hit another mirror segment first. So there's no risk that you get the, or very low risk that you get the wrong path lengths, get different path lengths than you think. Okay, so these were all the questions. So if there are no more, I would like to thank everybody for participating and also for the vivid discussion. This will be available on demand also on our website after the webinar concludes now. We'll upload it to the website. And of course, if you have any more questions on the product, let us know, and I'd be happy to answer that. Also the adaptions for ports and fiber-based solutions. Oh, just another question came in. Suggestions for mounting the sensor in a non-ideal situation. For example, roof mounting in line with feed tubes. So if this is about removing top and bottom lid and putting a tube instead of the lid, so that you just have a straight flow through configuration, I think that would definitely work. We actually have some customers who have been doing that with the first version cell. So yeah, I think that would work quite well. So as there are actually a few more questions coming in, I think I'd like to still officially close the webinar. Thank everybody for being here. In parallel, I'll of course continue answering any more questions that come in, but from now on it's only going to be answering the remaining questions. So yeah, thank you everybody for joining. Thank you also, Martin. And yeah, hope to see you soon at another webinar.